thank you very much, Mona, for your introduction, and for the PWI to have me today. I actually just got an email this morning as a reminder to pay my membership fee, so I better get that done. Yeah, as Mona said, I have 25 years experience working in transit. So one of my first projects I came across, light rail, was a highway scheme actually, where we replaced basically from one side to the road to the other side, replaced the highway, putting new cycleways in, and by doing that we also replaced the embedded track structure. And I was a young site engineer, and I learned firsthand how complex it is and what can go wrong, and that's part of my presentation today. Since then I learned a lot, obviously. I traveled a lot as well. And I think back to the question previously about young engineers and how can we sell what we do in light rail. There are lots of opportunities working abroad. I think it's just fantastic. So this is certainly, I think, something we should consider selling. About a year ago, I started thinking about how can I share my knowledge, which I've accumulated over the last 24 years. I started writing or developing a guideline for embedded track design to share my knowledge about design principles, about construction, what can go wrong, lessons learned from other systems. And today I'd like to give you a little bit of an insight on that work. So, as we heard from Marek early on, embedded track forms are a very common feature of tram systems. So I think it was 50% or so was the number here in Nottingham. And primarily to facilitate in-street running, obviously. Our colleagues in North America call a tram a street track, a streetcar. So that gives you some idea. Now, fitting picture here. So this is an intersection in Toronto. Obviously, a couple of years ago. That intersection has been replaced multiple times since. The traditional way of building it, as you can see, it's basically ballast track. They put it in, and the surface finish, in order to make it level, was probably, in the olden days, it was bricks, and then moved to granite sats, cobblestones, and the like, but nothing really special. Now, things moved on since then, and especially after the second stage of LRT systems coming in the 70s and the 80s and 90s, we moved away from building embedded track that way. And the typical way is we have a track structure, concrete, which supports the track. Now, there are things which obviously go wrong if you look around in some of the systems, not only in the UK, but all over the world. And we're talking about premature failures, or not the rails are wearing down, you have to replace it. It's more like things which go wrong much earlier than they should be. Why do those things wrong? So I'll touch a little bit on that, and then obviously lessons learned from other systems around the world, and how we could potentially implement them. So just in terms of track form, and you laughed about the green track, I put it in there, but we're talking about main four surface finishes, and it's really about what goes wrong on the surface. So usually the track structure itself, okay, anyway. The track structure itself does not fail as such. It's usually well designed. It's more like what happens on the surface finish. So we have the more functional surface finishes, which are basically concrete and asphalt. And then we have pavers and granite sats, which usually are required because of aesthetical requirements, urban design requirements. They're not necessarily facilitating heavy traffic, but pedestrians and the like. And then, just for completeness' sake, typically we group everything green track, cross track as part of embedded track as well, but we're not talking about those today because it's about in-street. So just a few pictures. I'm not blaming any particular system in the UK, but it's something which we see very, very regularly. So on the top left, we see.
I'll give you this if you'd like to wander. Easier.
Okay. Is it on? Yeah. On the top left, you see a typical failure on asphalt track. So what happens there is that the asphalt is not compacted well. This particular section is being operated by buses as well. So you have a lot of loading onto the weakest part of the asphalt, and that just crumbles away at some stage. What you can see in the top on the middle picture, you have a very open, coarse kind of asphalt, which, again, the issues with compaction, that's at the early stages. It has not failed yet, but all the signs are there that it's going to fail very, very soon. When we're moving to the right-hand side, those are the typical failure mechanism you see on pavers. And usually it starts at one paver, cobblestone becomes loose, and then it just spreads. On the bottom left, we have a picture from Toronto. So that was one of my favorite one here. We have concrete on either side. You see, you don't have grooved rail. In North America, typically the groove is formed in either in the concrete surface or in other ways. One of the reasons is that the grooved rail is just not available in North America, have to import it. But here again, part of the concrete failed, and then as you can see, the encapsulation system failed with it as well. So you actually end up with two grooves, which if you're thinking about being that a shared guideway with bicycles, motorcycles, a big issue. You can see in the bottom of the middle, so one of the ways to address the issues with building asphalt against the rail was to include those concrete shoulders either side in order to move that interface away. Now, you can see here even the concrete failed and had to be replaced multiple times. So again, that's something which we see very, very, very often. On the bottom right, that's a picture from a system in the UK where the operation on the track has not commenced yet. So that's you can see the white line here. That's a very awkward angle where the road crosses the track, and it has a lot of stress on that paving, and that just breaks with buses running over. So what's very, very important to keep in mind is that it's not necessarily the axle load from your tram or light rail vehicle that's about between 10 and 12 tons. If it's shared, it's usually the highway loading which causes the issue. If you think about your garbage truck, your fire truck, fire engine, and so on. So they are putting the heavy loads in. If you run in parallel with buses, so they are really beating your surface. Now, what are the main interfaces for embedded track? Just a cross section here on the right hand side, and that's again from North America. And you can see that the groove is not part of the rail as such. It's not grooved rail. It's formed in the encapsulation system. The red arrows, they're basically indicating all the potential path for water to get into your system, and water is really the enemy in all track form systems, from ballasted track to embedded track. And that's usually where the issues start. Now, what you can see on the left-hand side here, you see the concrete already spalling away, crumbling away. So with water getting in, sitting in there, not getting out, you have issues with frost damage. So that's an example from Toronto. Again, if you have different climates, obviously it may not be an issue, but that's something which we see very, very regularly. Now, talking about that interface, and that's really the critical one. It's the encapsulation system, and it comes in different forms. We have rail boots, as one component, multiple components putting together, or we have what you can see in the top right-hand side here, which is being poured in situ. So there are multiple systems out there for encapsulation system, but the three main purpose why we're putting in is it facilitates the rail deflection, because if you just pour concrete around your rail, the rail would not deflect. It's very, very stiff, so you rely on the suspension system of your vehicle, basically. So the encapsulation system provides that 1.2 to 1.5 millimeter of deflection on the load, so that's on purpose. Then we have to think about stray current mitigation. Obviously, in systems where we're running an OCS system, if you're running battery systems, ideas we hear from very light rail system where they don't necessarily have an OCS system, then obviously stray current is not an issue. But still, this is a main purpose, and also noise and vibration mitigation as well, as basically as a first step. To mitigate any noise and vibration. So those are the three main functions of the encapsulation system. Now, this is a critical part because this one here provides the interface between the rail and whatever is around the rail. So a lot of focus needs to get into getting this actually right. Now, when we dig a little bit deeper in terms of why is it so challenging to get it right. Now we found a couple of things, and yeah, this is not a construction site in the UK, by the way, so you wouldn't get away with that here. But anyway, in terms of contractual issues, we found. I mentioned previously in terms of the surface finish, where we have granite sets, pavers, that usually comes out of urban design requirements, and that causes a lot of issues because it makes the whole system very, very complex. There are a lot of movable parts, and it's very, very difficult to get this right. Now, we talked about earlier, or we heard about that early on, that specifically countries in Central Europe or Eastern Europe, they never got rid of their tram systems. So they maintained the expertise and the knowledge how to build track into roads, whereas if those systems have been replaced or have been taken out and have been put in later on, that knowledge in the supply chain is potentially no longer there. And that causes a lot of issues, obviously, in terms of, yes, you have a contractor doing your highway works and a track contractor doing the track works, but not necessarily understanding the interface between the two. Often what we also see are requirements for track replacement, where in the design you already have to take into account how to replace it for if your rails are wearing down and so on. But that sometimes leads to a compromised design where you try to address both, like it needs to be as longevity and design life as possible, but also easy to replace, and that usually doesn't work. So it's either the one or the other. Now, there are some approaches on transit systems we've seen where, in terms of replacement, when it comes to track replacement, and basically everything is being replaced, not just the track, but also the track structure underneath, which may actually make more sense than being in that cycle where you have to replace or address some of the issues prematurely because certain elements fail. So that's something to think about. And then one other thing we found was the relationship between the construction and the maintenance in the PPP contract, where the contract, obviously, even if it's the same overall company as the maintainer, the contractor is very, very eager to get the thing in, get it in cost effective as possible without necessarily thinking about their colleague in the maintenance who have to maintain it for the next 30 years. So there's a lot of breakdown there as well. In terms of general technical, now the whole thing should be considered as a system. So you have your rail fastening system, you have a rail, you have an encapsulation system, any joints or whatever you have. So it's a system, but often enough, it's not approached from that point of view. Individual elements are being purchased and being coupled together without fully understanding how they're working with each other. The other thing is, as I mentioned, the lack of familiarity is just because we lost that expertise. And we're dealing with highway contractors. They know how to put granite sets in, but not necessarily appreciating the difficulties which associated with building next to a rail, which moves, right? And then also we have the contract interfaces where you have one contractor building the track, the other one building the highway, and there's friction and an issue with communication between the two. Commercially, in terms of warranty, I mean, usually what you get warranty for a particular product, but not as a system. If you buy 5 different things, putting it together in a system, you won't get warranty. So you just end up with having to replace certain elements at some stage outside the warranty. In cost pressure, in terms of sourcing the cheapest, for better use, for the cheapest material. Now, why does it fail? I mean, there are obviously a lot of reasons. There are obvious ones where you may have a contractor is not familiar with the type of work and so on. But what's also often enough been overlooked is some of the loading or what actually happens in the track structure. Now, on the left-hand side, what you can see here, this is a day after it rained, and you can still see the water splashing. So you actually have the water sitting between your encapsulation system and that concrete shoulder, and whenever the tram runs over, it's basically pumping the water in and out, but it never gets out completely, right? So you have it sitting in there. Now, on the top right, you see a cross-section for track finished with granite pavers, and it's not only the loading you have longitudinal, but what you have in terms of the vehicle loading, and as that it's not only the streetcar, the tram, but also your rubber-tired vehicle running over that. Because the encapsulation system provides that deflection, you have the vertical the interface between your rail and your embedment layer. You have the forces there, but you also have a slight rotational force because the way the grooved rail is set up. So that's all you need to consider, and there has been a substantial testing done over the last 20 years on different finishes and how they perform. That's obviously there's a lot of knowledge out there, but not necessarily being adopted all the time. What you see on the right-hand side at the bottom, it's one of those standard web filler elements, which basically sit in the web, and then your surface finish is being installed against it. Now, the issue is with some of those materials, they're not stiff enough to accommodate all the compact. For example, if you're putting a bituminous pavement in, the compaction, you can't compact it because of the flexibility of that type of material. So that's again something which we see very, very frequently. Now, some of what we can learn from other systems. Now, on the left-hand side, that's one of those typical scenarios where the bituminous surface was not compacted properly, and with the loading from vehicles running over, it basically moves into the web and fails and would need to be replaced. Now, when we looked into one of the level crossings here, embedded track in Dublin on the right-hand side, and that was back in 2008, 2009. We did not want to build that concrete shoulder. We thought, well, is there a way to build asphalt against the rail like a standard practice in the likes of Germany, Austria, Switzerland, all over the place, and it works. So we looked into the design guidelines and the design approach and how we can adopt this to the Irish design manual for roads and bridges. It was actually quite, because some of those products which are used in other systems design, they're not readily available or they're not approved for use in the UK and in Ireland. So that was obviously one issue, one barrier we had to deal with. So this was then suggested after research, and that's a picture from 2 years ago. So it's still holding up quite well. Now, I mean, there's obviously a danger if we're adopting systems from other places. So when you think about what happened in Edinburgh, for example, before the system went into operation, a lot of the embedded track had to be dealt with before the first tram ran over it. And again, that was adopting a design which works perfectly well somewhere else, but the type of bituminous mix is just different and is not available in the UK. So therefore, you see that if you take one of the components as part of the system no longer works, the whole system fails. So that's obviously a very, very important lesson to learn, that you can't just blindly adopt from other systems. Now, example here, if you're talking about pavers and granite sets, I think the key message here is that what you see on the right-hand side is just that experience which exists in the supply chain. They know how to install it so it lasts. I think that's very, very important. So the experience is there. It needs to be implemented correctly. And then also on what you see on the left-hand side, obviously that's the worst angle I think you can have a crossing over rail. You have those very, very small pieces of pavers. They're not in any way secured enough to hold up. Now, in conclusion, I think that there's 3 different things we should think about. Now, on the left, a picture from Dublin again, you can see that a concrete shoulder, what we call it, or concrete nib along the embedded rail. So that basically moves that interface between your granite pavers away from the moving rail and basically moves it outside. But then you end up with that concrete surface, which often enough is not necessarily meeting urban design requirements, but that's a way to deal with that. If you know, okay, well, that's one mitigation method you can think about. The thing in the middle here, a picture from Vienna. Now, why did I put this one up? It shows, yes, you have reinforcement and everything there, but it's a very simple system. It's a concrete surface. It will be brushed concrete or imprinted concrete. It doesn't mess around with granite sets or pavers or whatever. It keeps it very, very simple. And if you look at some of the historic buildings in Vienna, it doesn't really matter. So I think rethinking the whole urban design requirements, I think it's something which I think should be considered personally, and with regards to keeping maintenance in mind, because in the end it all comes down to, if you have to replace it, if you have to go in, you have to close the line again in order to do any repairs. I mean, this is obviously a major impact to your traveling public. On the right-hand side, that's just a detail of embedded track in where you again have granite sets, but it takes into account the additional movement you have to deal with. And there's always the discussion about, should we put it on sand, should we put it on concrete, how stiff should it be? So that basically takes all this into account and specifies the joint filler as well on top of your surface. So again, that's more adopting best practice from other systems in terms of if you recognize there may be an issue with the quality of work, how can you remove that how can you move that interface, how to simplify your design and construction, and how to use that experience which is out there in the LRT world. Yeah, so that's about it. Thank you very much.